Okay, hi everybody. Thank you for joining another tinyML talk. My name is Jenny Plunkett and I'm from Edge Impulse. And today we'll be hearing from Semir Haddad, the Chief Product and Security Strategy Officer at MicroEJ, and he'll be presenting on integrating and deploying machine learning at the edge with embedded software containers. Thank you to our tinyML strategic partners for committing to take tinyML to the next level together. AZIP, Analog Devices, Aeon Devices, Arduino, ARM, Deep Light, Edge Impulse, PhotoHub, Greenwaves Technologies, Gravity Inc., IBM, ImageMob, Itemis, Clickatech, Microsoft, Noda AI, NXP, OctoML, Prophecy, Keekso, Qualcomm, Reekson, Renesas, SAP, Schneider Electric, SensiML, Silicon Labs, Sony Semiconductor Solutions Corp., ST, Stream Analyze, Synaptics, Sentient, and TDK InvenSense. Join our growing tinyML communities on meetup.com and on LinkedIn. Our meetup group has over 12,000 members in 46 groups in 37 countries, and our LinkedIn community has over 3,000 members and 10,000 followers. Join here with these links or with the QR codes. Also subscribe to our tinyML YouTube channel for updates and notifications. This is also the channel where today's talk will be uploaded on youtube.com/tinyml. There's over 8.5 thousand subscribers, 500 plus videos, and 284,000 plus views. Our next tinyML Trailblazer series with Luca Vere is live online on January 25th at 7:30 a.m. Pacific time. Register now with this QR code. The next tinyML Summit is coming up on March of 2023 in person in California at the Hyatt Regency San Francisco Airport. Registration is open at the link that you see on the screen, and sponsorships are available at tinyml.org, sponsorships at tinyml.org. It's an in-person event, and it will be held in conjunction with the tinyML Research Symposium. The Research Symposium is the premier annual gathering of senior level technical experts and decision makers representing the fast-growing global tinyML community. The call for papers is also open. The tinyML EMEA Innovation Forum is in 2023 as well in June in Amsterdam in person. The call for presentations will open this month, and more sponsorships are available at sponsorships@tinyml.org. Today's speaker is Semir Haddad. Semir is the Chief Product and Strategy Officer at MicroEJ and is in charge of product strategy and ecosystem for the company that makes everything software defined. Semir has over 20 years of experience working with the industry leaders and startups, bringing innovative technologies to industrial and consumer markets. Early in his career, he worked on digital video and audio, creating the first DVD player and developing one of the earliest PDR software solutions, for which he received 4 patents. At ST and Renesas, he drove the creation of award-winning lines of microcontrollers and microprocessors, including the STM32, RX, and RZ. Recently, Semir was part of the innovators at Etacompute that created one of the first tinyML implementations. Semir graduated from Central Supelec with a Master of Science in Electrical and Electronics Engineering and from ESSEC/Mannheim with an MBMA. Semir, take it away, and thank you for joining us today.
Okay, thank you very much, Jenny. And good morning, afternoon to everyone. I think we may have people from Europe as well. I'm speaking from the US and from San Francisco. So today we're going to look at how we can integrate and deploy machine learning at the edge with embedded software containers. So my talk will be, in fact, will follow 3 steps. So the first step will be I'm looking at tinyML from product owner's point of view, which means that tinyML is cool, it's very interesting, everybody likes it, and everybody in this audience, I think, is very excited about the technology, but how can we use it in a real product? And this raises some question about integration and deployment that we're going to cover. And then I'm going to talk about a DevOps solution, which is containers. So the concept and origin of containers, software containers, and how they can be made edge compliant, even if the technology was originally designed for the cloud. Now it can be available for edge devices. And at the end, so I will explain what is an example of container for HML, which with our solution from MicroEJ. And show the concept and implementation, more details about the implementation, the technology, and I will end up with a demo with our partner Ozone, which is an AI company that we work with. And we will be good for the Q&A at the end. So to get started, a very quick introduction about MicroEJ. So we are basically the company making the tiny container for the embedded world. It's called MicroEJ V, Virtual Execution Environment. That's our main product. So we are a software company and we are an IP provider. We license this tiny container for companies that build products. We have invested $40 million in R&D in total since the inception of the company. We are global. We have offices all over the world, US, Europe, Asia. And to date, we have I would say, sold more than 150 million units of this software container license. So just to give you an idea about the scale. We, in this audience, I think we are all aware that the demand for smart devices is exploding. So these are numbers from various sources. For instance, some people say that there will be 75 billion connected devices by 2030 in the world. The smart home sector is growing 20% per year. We know that also with the new technology coming like 5G, more and more capability will come to the end device. When we talk about smart devices, also this audience is pretty aware what we're talking about. We're not talking about gateways or servers and so on. We're really talking about the end of the network, which is all the small devices that that are around us in everyday life. So from home to appliance, factory, buildings, all these very small devices you have everywhere. And with this proliferation of intelligent devices came the concept of distributed intelligence. And tinyML is exactly that. It's distributed intelligence. It means that you run more software and more intelligence, more awareness at the end of the network in the small devices. So I'm pretty sure you're all also very convinced of the advantage of this because it comes with 4 main advantages. The first one is it reduces the cost of data transfer and data storage. So everything is done locally. All the processing is done at the device level. It reduces also the energy consumption and carbon footprint of the system because you don't have all these transfers from cloud to edge. It improves also the service latency. So it's a very tangible effect for the consumer and the user is that you will have fast response locally because all the AI is done locally. And then also it increases the resiliency of your system because the devices don't need a cloud connection to perform their operation. So these are very tangible advantages of having tinyML and distributed intelligence at the end device. So this is why you need tinyML, and this is why everyone here is very excited about tinyML. But the other question is, where do you need? And when you think about devices and things, these are really this slide shows what type of devices we're talking about. We're talking about a variety of devices in all kinds of market and segments, doing all kinds of functions. So we could look at home appliance with cookers, washing machine, fridge, coffee machine even. You can think about smart home with camera and thermostat and even smart plugs. And we can think about medical device. We can think about robotic vacuum cleaner, smartwatch, and even the big thing on the right, which is a windmill. It can be thought of as a end device, an edge node, and it can run tinyML as well. So now you are talking about, okay, we want to deploy tinyML. We want to have tinyML on these devices. And I'm giving an example here for a smart cooker. So we have a smart cooker. We want to add some intelligence. We want to adjust, for instance, cooking versus the type of food that you use. You want to also learn the user's preferences in terms of cooking. You want also to maybe have some advanced cooking cycles that can cook the food exactly as it needs to be cooked. Okay, I don't know, but I think people that design cookers will have lots of ideas. But the point is that if you design a smart cooker and you add tinyML to it, it still needs to perform its main tasks. And the main task is to cook, to manage the heating element and mixing, even if you have a mixer inside the cooker. It also needs to manage the display, the user interface. So you have all the button and display and so on, and maybe sound. And it needs to connect to the cloud. It's a smart cooker, so it should be also a connected cooker. So you have all the task of connecting and getting information from the cloud and so on. So what it means is that tinyML is an addition to the existing functions of the device. And that's what we see with all our customers. Basically, they already have a product and they just want to add the function of tinyML. So tinyML must integrate with an existing device, and tinyML must be easy to deploy and update. And that's the one of the challenges with tinyML and maybe the tinyML adoption, because when we think about tinyML, we are very focused on AI. So what is this AI process? And this is a depiction of the AI process that you will certainly relate to. So we have a cycle of defining, getting the data, understanding the data, designing the model, then training the model, optimizing, validating, releasing, and then testing on hardware, and going again in the loop until you get the satisfactory result. So this is your process of developing the tinyML and the AI model. And at the end of this process, you get the train neural network for the edge. That's, let's see, the holy grail. That's really what you have been working for. I want this very tiny AI that can run on an edge device and does exactly what I want it to do. So that's great. And that's the focus of basically most of tinyML talks these days. But it's not all, because at the end, you want tinyML in a product. That's what you want. That's what you want. You want it to be deployed. And it means that this product already has lots of software. So lots of software and hardware. So I'm showing here for instance, a depiction of what you would have for this smart cooker. So you have the hardware, you have the processor, and then you have an RTOS or maybe Linux, I don't know. And then you have a BSP with drivers. You have lots of also functions, software functions that are already implemented. And then you have the application with lots of, for instance, cloud clients or display application and so on. So lots of stuff already exists. And then you come with your neural network. And then with the neural network, you say, okay, I need to execute it. So there is certainly a neural network runtime that you need. It doesn't execute alone like that. And then you want to insert this into the existing software. And The other thing is that this neural network has lots of dependencies with the rest. So it has dependencies with the BSP, with the memory needs and performance need and so on. It has the dependencies with the network because it may have to, you want also to recollect data, or you want to also update the neural network. It has dependency with sensors because you get the data from sensors, and that's where when you get the output, and then with the application, of course. So lots of dependencies, and you insert that in the application. And that's where really the hard work starts, because then you enter the realm of embedded software, which is quite complex. The embedded software aspect, the embedded software development has lots of constraints. So the first thing is that when you enter embedded software and you want to deploy on a real product, you have what you call the matrix of pain, which is you have hundreds of variants of processors. It's not standardized, unlike, for instance, PC. So you have lots of variants of processors, tools, software components to address. And you want your neural network basically to work on many products. The second thing is that you have also lots of objectives when you design for the embedded. You want to have very good quality, because every product we're talking about, they're supposed to work very flawlessly. It's not again, it's not like a PC when you can reboot. It must be also real time. It must be high quality, but also it must be flexible. And then you have also lots of optimization constraints. Your tinyML and neural network has been trained, optimized, and so on. But then it becomes an element in a bigger system that has cost, power, memory, and compute optimization issues. So you need to balance all that. And then the last but not least, when we're talking about embedded, there is a talent shortage these days. So most people that get out of school, they want to go now for design web software, or they want to design cloud software. They really don't want to do it into embedded. And so there are not many people that are still knowledgeable about embedded software. And then you combine that with the application, and then you combine that with machine learning. So finding the rare bird that has all these this understanding of embedded application and machine learning is very difficult. So, but what we are saying here is that neural networks, in fact, are software. And if you want to understand that and to picture that, you can look at this slide with a comparison. You have if you look at neural networks, you have code, and this is basically your neural network. You have data, that's your weights and your parameters, and then you combine the two, and then it gives you a result. That's typically a detection. Okay. And then it's very similar to what you can have in the, for instance, graphic user interface space. I'm showing here an example with rendering a font with a vector graphic engine. So you have code. Okay, again, that's the code that describes what you want to do with your fonts. You have data, that's your fonts, and then it gives you a result, and it's a display on the screen. So from an execution point of view, a neural network is just software, just another type of software. It may be, you can see it as a domain-specific language, but it's still basically a software. And if you're not convinced of that, think about how you execute TensorFlow-Lite micro software. So basically, you have your trained model. The trained model is converted into a TF-Lite file, and then if you follow the process of TensorFlow-Lite micro, then you convert that into a C array, And then this is after that interpreted by the TensorFlow Lite interpreter. So it's really like basically Python code or Java code. It's interpreted, and then it generates the it's just used by the application code. So keeping that in mind, that neural networks is software, then you have the same constraints as software and you want to manage it as software. It means that you want to be able to maintain and update software with the rest of the software. You want to maintain and update neural networks with the rest of the software. So we want it to be integrated in the DevOps process. You want to use configuration management, continuous integration, continuous deployment. And then you want to have the same lifecycle management with a secure and safe update in the field. So this is a summary of the challenges that you have when you want to deploy neural networks, and especially tinyML. So how did cloud solve the problem? So I just get a quote from Google Cloud here. It's, they say, even in the cloud, machine learning projects require you to manage compatibility, complexity of a never-evolving software stack, which can be frustrating and time-consuming. That's exactly what we just described. So you have basically it's software, and you have to manage it as software. And what Google Cloud decided to do is that to use deep learning containers to ease the process. And if you look at Microsoft, what they did, they used what they call the Azure Kubernetes services, which is a combination of orchestration and containers to manage machine learning. So what you're talking about here, it's containers. And containers, what they are package of software that contains all the necessary elements to run in any environment. I'm again mentioning a quote from Google Cloud. And containers virtualize the operating system and run anywhere. Okay, so that's kind of the basic concept of containers, that you have in one element of software all the dependencies and all the elements necessary to run your software, and then you have this idea of being able to be very portable. So the advantage of that is that it becomes very portable and consistent on all your target. So in the case of cloud, it can be cloud or on-premise. It encapsulates all the resources that you need. So you have much less dependency. You don't have to, when you're concerned about your neural network, you're not concerned about the rest of the system, and if you're not taking too much resources and so on. And then also, it can help you deploy multiple instances of these containers. So that's very useful for cloud because you have lots of microservices that you can scale up and down. And at the end, also, it brings you the capability to do fully automated DevOps, or what they call ML ops. Okay. So can we apply the same principle for tinyML? We can, but so what we would like to do to see for tinyML, we would like the same idea of having cloud native development, the concept of microservice or micro apps, the concept of containers with agile development, DevOps, virtualization, all these concepts apply to the edge. So there are two ways to do it. The first way is to do, okay, yeah, let's use these technologies from the cloud on the device. And what it means is that, okay, you have to bring Linux, Kubernetes, Docker, and so on. And it's not practical. It's very expensive. You need to have a very powerful device to run all that, lots of memory. It wastes a lot of energy. So basically, it's not applicable. If you look at our smart cooker, there is no way the smart cooker can run Kubernetes, you cannot sell it. It would be like a $2,000 cooker. No, what is the best way to do it? It's to start from the device. So build a platform, let's say a low power container technology for the edge from the ground up, from really design for the end device, and with container and containerized app that allow like this microservice development and micro apps development, and also the capability to virtualize the hardware so you can ensure portability and the best use of any hardware platform. And this is what we have done at MicroEJ. So this, once you have the containers for tinyML and you containers for the edge, it brings exactly the same benefit that you had with the cloud. So portability and consistency. So you can work on a workstation, you can work on a device, or you can work on any device, and you will have a consistent behavior of your neural network, and you don't have the problem of optimizing or let's say or retuning the neural network for each device that you use. You encapsulate all the resources that you need to run the neural network, so you abstract, in fact, the physical resources. It makes it very portable. And then you can have also multiple instances of your neural network. So for instance, sometimes the neural network is very optimized, but it's very tied to the runtime. And if you want to have a second neural network running at the same time, you have to duplicate everything, but then lots of complexity comes into play. With the containers, you can have just multiple instances. And then you can also update and manage models like software, very flexible way, with a very good, very easy development and post-release upgrades. And then at the end, you can manage software, the same neural networks as software, with the ML being integrated in your CI/CD process with these containers. So I'm going to now explain a little more about the technology and how it works. So this is a view of, I would call it a block diagram, even if it's not hardware, but it's a good way to understand how we do it with MicroEJ. So this is a view of our software container. So what we do, in fact, if you start from the bottom, the hardware. So we have the processor core, which is every one of these devices in the edge has a processor core. We run on top of that the real-time operating system. It can be an RTOS, it can be Linux, for instance, or even QNX, but most of the time it's an RTOS. And then you have the BSP with all the drivers that support the hardware, and that's basically the low-level drivers that you need to provide all interfaces to all functions and peripherals in your hardware. And then on top of that, we run what we call our Mesh 32, which is our virtual core. So this is basically the core of our technology. It's a virtual core that abstracts the hardware, and that make it possible to have on top of that what we call managed code, which means that all the code that runs on top of the Mesh 32, on top of the container, is abstracted from the hardware. It's independent code from the hardware. So we have on top of that lots of libraries that we bring that bring the basic function, but we are now in the managed code realm, which is really abstracted, really it's high-level software. So we're not talking about interfacing with, for instance, an Ethernet controller, but we're more talking about opening a socket. That's basically the concept. And lots of libraries that can sit on that. And basically, we use open source libraries. So all these libraries are open source, and we can use the open source libraries Then you can, with this containerization, you can have also mini containers we call applications that run on top of that. So you have these applications are all self-contained, independent, and protected. So, and that's how you build a tiny container for the embedded world. So what it means is that this technology allows to have software that becomes independent from the hardware and in large proportion. And it means that you can run, in fact, on a virtual device on a PC because it's, again, abstracted. So the same code will run on a PC, or it can run on any device that has the container, the software container. And the application can be safely provisioned and ported to any device. So if we put that in the context of Edge AI and tinyML, we use the same concept. So we say, okay, the previous slide was about any kind of software, and we say, okay, machine learning and neural network is software. So that's the same concept. We use it as software that is inside a software container. So you still have your model design and training, of course, that's your task that you keep. And then you generate your neural network that is tinyML neural network, perfectly optimized for the edge. Then from there, in fact, you generate your neural network file that is containerized by MicroEJ. So we make it an app that is an independent app, and that can be then updated remotely without rebooting the device. That's important. So it's just an application that you install and that you can remove and that you can start and stop. And then it communicates with the rest of the app. And you will have, for instance, a cloud agent app that can report information from what's happening at the edge. So typically, that's I would say, the virtuous circle of what you want to do for tinyML. So you design your tinyML, you deploy it in a container, and then you report information. And then when you have some I would say data anomaly, or you use some training, so some detection issues and so on, you can detect. You can send more data to the cloud to continue your training and improve your neural network and after deployment. So that's the concept that you will be able to also update and refine your tinyML after you have deployed in the product. So if you look at the integration, how we integrate this neural network in the MicroEJ framework, so it's you have your trained neural network as an application, and it sits on top of an AI library, and then this runs on an AI engine, and the AI engine here it's basically an abstraction of the hardware and an abstraction layer. And it can be also, what it means that we can also support either hardware acceleration or software implementation. So typically, because your neural network just runs on the top in the container and top in the managed code, the neural network doesn't know if it's hardware accelerated or software executed. Just there, and it will be consistently deployed in all devices. And some device can have hardware acceleration, some device can have just software execution, but it's the same from a neural network and software point of view. And you will also be able to test your neural network integration in the device on a simulator. So that's what most of our customers do for any software development. They test and they basically develop and validate all the software on a simulator, on a PC, before they deploy it. And you can do the same with the neural network. You will be able to test it and simulate it and then validate it even before it's deployed in the hardware. And after that, it's just a deployment issue. The neural network, the container itself is binary code that you just deploy, and it runs the same on the simulator and on the hardware. So as I mentioned, this is an example of the advantage that you can design neural network once and you run everywhere. So basically, your containerized neural network run on desktop, on the simulator. It can run on a device. I'm showing an example with an ST device, for instance, here. Okay, this device. And it can run on another device. I'm showing another one, another processor like the NXP RT595 here. It will run the same. And it doesn't even know that, for instance, on the ST device, there is no hardware acceleration, while on the NXP one, there is one. So from the point of view of the software and the neural network, it's just the same. But on the implementation of the virtual execution environment, in one case, we have hardware acceleration. In the other case, we have just software implementation. So these containers, these small applications, are safe and secure by design. So I'm showing here a little more detail about how these applications are managed. So we have, in fact, in the MicroEJ virtual execution environment, we have an app orchestrator. Okay. And this app orchestrator, it's a kernel function, provides an API and resources that are available for the apps. And the apps cannot access directly anything that they are not, that they have to go through the core. And then also they cannot bypass the core. They cannot go directly to the, I would say, BSP and low-level software. And there is no memory dependency between the apps. Every app has its own memory allocation. And then it's all fully managed in binary. So there is no recompile, I would say, or for the binary is deployed. That's the binary that is deployed and that is compatible from one implementation of the container to the other. So basically, it's like on the, I would say, your Android phone, you install, you uninstall, you start, stop apps the same way. So yeah, it's so this is more detail about this process. So basically, the app is developed and you're talking about, for instance, your tinyML neural network is developed. You generate binary. The binary, in fact, when you install it on the virtual execution environment, it's verified. There is a code verifier technology that has been demonstrated formally. Is based on the Java virtual machine technology. So the code is trusted, and when it's trusted, the code is the application will execute within the access right that have been assigned by the system. So basically, there are runtime checks, make sure that it cannot go outside of the boundaries that have been defined by the app. Okay. But even if the apps are safe and secure, if they can, they have their own limited space, they can still provide services and access services. And we have a mechanism, in fact, to share APIs, so going through the kernel. So an app can share some API, and also they can share services. So basically, an app like the neural network will provide the services for detection, and it will get the services from, for instance, sensor information and so on. So this is kind of it for the, I would say, theory. Now a little bit of practice. I'm just showing now, I'm going to show a small demo with one of our partners, so Ozone. Ozone, it's an AI company that have developed neural networks, lots of neural networks, and runtime for neural networks. So they're partner for first, and they're also a partner of NXP with it's one of our partners, semiconductor partners. So we did with them the integration of the Ozone runtime inside MicroEJ, and that's the first implementation of containerized AI. So I'm going to show you this. If I can get to the video, here it is. Okay. So that's the video. So I did a video because, you know, doing that in live would be difficult. So you can see here on the right, I have my board showing, in fact, I have a camera on the board. It's an NXP board, RT1170. I have a camera on the board. I'm doing some acquisition on the camera, and I have a screen that shows the result of the acquisition. So the demo is a face detection demo. So just a simple demo. And on the left side, I've got the IDE from NXP where I built the demo just to show you, so you can see on the left side the project itself. So just showing the MicroEJ files and the Ozone file together. So I'm going to now to start the video. What is doing, it's loading the code. Okay, of course, we have not done the deployment on the cloud and so on yet, but just the integration. So I'm showing that I'm just loading the code on the board, and the middleware is starting, MicroEJ is starting, and then we're doing the detection. So detection, you see the faint blue, red box around my face. Yes, it could be a little more visible, but you certainly see it. So this is basically a face detection. You can see here it's working pretty well. And the AI itself is classic AI. It's pretty fluid. It's a good performance from the Ozone runtime. But the main idea is to show you that, okay, this is AI, but it's also combining the MicroEJ container with AI. That's the concept here. And I'm even doing some fun test at the end with my cat, just showing that this is not detecting the cat face, just a human face. And that's a good, it's a good algorithm. Okay, yeah, the cat face is not detected, definitely. Okay. Okay, so that's it for the demo. So yeah, we showed this face detection with Ozone and MicroEJ. So if you look at what the demo does, in fact, it's like you have all the model design and training with the deep view tools from Ozone. So they have this very nice tool chain for neural network design. And then you have also, once you do that, you generate the neural network. So what we did in this demo, it's not completely this process, but that's the concept of the process, that you generate a containerized AI, and then you do the event detection and so on. In this demo, we put the MicroEJ container and the AI together. We did not do the app deployment yet, and this is the next step for us. So that's the concept of what we will do ultimately. So the neural network will be trained. It's a trained model that is deployed in AI, and then you have the runtime that is integrated at the bottom. In addition, of course, you can have also any kind of neural network. So I'm showing here the face detection, but also has lots of models that you can use, and lots of also services to design your own neural network if you have some specific ideas. So that's a summary of what we have seen today. So with a tiny container for tinyML, post-tiny, you can have a very seamless process in designing, integrating, and deploying neural network. So the design of the neural network then can go directly to the development that can do integration and validation on a simulator, and then deploy seamlessly as a small container to the MicroEJ environment. And then this can help you integrate your neural network into the full software process with CI/CD, which is the golden standard for software deployment. And that's it for today. Now I'm opening for Q&A.
Great. Thank you so much, Semir, for that great presentation. We have a bunch of questions here in the Q&A, and as we're going along, please feel free to ask more questions there, and we'll get them answered. But the first question is, what is the best way to calculate latency on the hardware?
What is the best way to calculate latency on the hardware? I think it's not a question completely related to our tiny container. I think it's a question overall for all tinyML implementation. Yes, the answer is that you measure typically. You have timers in your software, in your embedded software. If you have a real-time OS, you have a timer tick, so you can just measure the latency by using the timing function of your real-time operating system, or by using, in our case, if you use MicroEJ, we have also a timing function that are at the top level in the container.
Great. The next question is, which barriers exist to perform containers and bare metal devices without an OS?
Okay. So it's not without an OS. We usually always have a real-time operating system. So, but the main barrier, if you think about implementing a tiny container in a real-time operating system environment, compared to, let's say, Windows or Linux environment, the main barrier is really about resource optimization. So basically, you have memory and performance constraints that you don't have with Linux and Windows systems. So you need to be careful, and that's why, in fact, that's basically at the end the main, I would say, advantage of technology like MicroEJ is the optimization. We are very tiny. Our container is only 30K bytes of code, compared to megabytes if you use Docker containers, or if you use anything like that. So it's really starting from the ground up, from the embedded space, and optimizing for the embedded space. So that's the main barrier. Yeah.
Great, thanks. And then we have another question. Looks like their first question was, can the containers leverage hardware and accelerators? But then they said that it was mentioned. So their follow-up question is, do you have a list of supported accelerators, and can third-party provide drivers for supporting custom specific accelerators?
So I don't have a list for supported accelerators yet. We are just starting to implement AI with MicroEJ, and the first one is using the runtime from Ozone, which has been a good partner. Definitely we are very flexible in terms of acceleration. So any kind of acceleration can be implemented. Once you have the abstraction level, if you remember my block diagram, at the end we have this AI abstraction level that we have for the hardware. Then it's very flexible and can be easily ported to one accelerator to the other. Most accelerators are very similar in terms of what they do, what they perform, and just doing calculations very fast, but it's all the same calculation, so it's pretty easy to abstract.
Cool. Do the containers penalize the inference performance of the models? And if it does, how much does it?
So do the container parallelize the inference? Okay. This is not per se the container technology. It's more the optimization technology that you do at the neural network description level. But definitely we can implement any parallelization that is developed by let's say that is performed by the neural network description. Yes.
Great. And then the next question is, they want to know, what is the current microcontroller hardware currently supported by MicroEJ?
So we support a broad range of microcontrollers and microprocessors. You can check that on our website. So basically, all the major microcontroller providers, ST, NXP, Renesas, Espressif, and so on. We are very, I would say, agnostic in terms of hardware. We support Cortex-M, any kind of Cortex-M cores, by the way, but also RISC-V and other architectures. So yeah, it's we are pretty flexible. The demo that I showed is done on the NXP RT1170. Which was a device, and yeah, we chose because we are a gold partner with NXP, so we have very good support from them.
Great. Are there any plans to make the MicroEJ SDK available to VS Code? And also, does this SDK support multimodal ML approaches in the supported hardware?
So there is a plan to so right now the MicroEJ IDE is based on the Eclipse. Okay. There is a plan to, and we have also some version for Android Studio. There is a plan to make it, in fact, yes, more flexible. So we are planning to support Interleaf and Gradle. Not Interleaf, sorry, IntelliJ and Gradle built, and we'll have also a full command line version that can be used with VS Code, but it does come later in this year, not yet available.
Great. And does the SDK also support multimodal ML approaches on the supported hardware?
I'm not too familiar about this.
Maybe they mean multi-model? Yeah.
I don't know what it means. Maybe I can, if you can send me the question, I can check with my team later.
And Semir's email is listed on the slide that's been up the whole time, so feel free to reach out there. What is the effort needed to adapt MicroEJ 32 for a given platform?
So if by platform you mean any kind of hardware, it's minimal because as I said, we already support most of the processor cores that exist at Cortex, all kind of flavor of Cortex-M, and even we're starting to support also RISC-V. So if typically you have a processor that is based on Cortex-M, it will be a matter of weeks. If it's a processor that is completely new with a new core, with a new compiler and so on, it may be a little more involved, but we can discuss.
What's the overhead in memory that you have to add to have this abstraction? For example, if I have an ARM M4, what is the difference in memory if I port the NN manually or via MicroEJ?
So for the neural network itself, the overhead is minimum. And the reason is that basically you are you understand there is a managed code and there is the BSP, and the managed code is basically the description of your neural network, and it's the same whatever approach or code you use, and then the most of the execution is done by the AI API and by the AI engine that you have inside the MicroEJ virtual execution environment. And this is pretty much optimized. That is really developed for a specific target and so on. So at the end, the overhead is minimum. The overhead in performance and code size is minimum.
Great. And sort of going along with that, are there any minimal memory requirements for the containers? Would it work within 256K?
Yeah. 256K is basically the starting point for us. So it's not for technical reasons. As I said, the code size of the mesh 32 of the core engine is 30K only, of 30K byte of code, so it's not much. But then after that, when you add the various functions that you need, usually you add you will need 128K byte of code minimum to do an application, but then you don't do much. So 256K is the starting point. So yeah, it could work with 256K.
Great. Does it rely on AI frameworks such as TF-Lite?
So the MicroEJ container is basically a technology to deploy and encapsulate and integrate your neural network into your software. So it's not dependent on any, I would say, process that you use to generate the neural network. At the end, you have a neural network description, and then we just execute it.
Do you support Jetson Nano?
Jetson Nano. So Jetson Nano is an NVIDIA processor. We don't yet, and it's not really a tinyML. I would say hardware. Usually, it can be embedded, but it's embedded very. It's a very powerful and very, I would say, with lots of memory. So yeah, we could, but I don't think there is a good use case for that.
The next question is, on hardware, do we deploy containers directly without an OS? If yes, what is the OS that they use?
So again, we have to define what we mean by OS. Usually some people, when they come from the cloud, when they think OS, they think Android, Linux, and Windows. That's what they call OS. But in our case, we always use at least a real-time operating system. But these are more like FreeRTOS type of ThreadX type of OS, because just it's easier to implement the container on top of an RTOS. But you don't need Android, Linux, or Windows.
Great. What embedded RTOSes can MicroEJ run on? Memory or processing requirements as well?
So we run on a lot of RTOS. The most popular, of course, are the one that you know, FreeRTOS, like Azure RTOS, and ThreadX. But we are also relatively agnostic in terms of real-time operating systems. So most of the popular ones are supported.
Great. just 2 more questions left, and then we'll be done. If multiple edge devices need to communicate internally or via the cloud, do we use any network interface or protocol for the services with MicroEJ?
Yeah, we do with like basically it's MicroEJ is a way of implementing a function. So the same function that you want to implement, you can implement it with basically Android, or you can implement it with code that you write yourself, like bare metal code. It's not very efficient, of course. Both ways are not very efficient. And if you implement it with MicroEJ, and you can have you will implement just the same function. So basically, connecting a device to the network, you will have a TCP/IP stack. You will have a network agent. So we have our network abstraction we call net, which is basically you open a socket and so on. We have SSL, also we have security on top of that. And then you will have certainly a cloud agent. So if you have Azure, you have Azure Cloud, and if you have Google Cloud, you will have your Google Cloud agent and so on.
Great. And then I guess there's 2 more questions, but I'll just do one more.
Yeah.
What should be the best tools in TML for algorithm scheduling at the edge in order to assign priorities and tasks?
So so if I rephrase, what are the best tools to assign priority and tasks for tinyML? Is that the question?
Yes, I think that's what they meant by TML.
Okay, tinyML. Okay. So it's difficult to answer because these are the same tools that we use for any software. Basically, so you have lots of tools to manage the priorities and tasks. For instance, we have System View from Semir that is pretty good. That is a real-time tool. You can get trace from your code, and you can analyze what your tasks are doing, and which one is executing at any time, what length of time they do. So there are lots of tools like that. And these are more embedded tools. So you have to think about, you have to, and that's what the message also I'm giving today is that when you're talking about deployment, you have to switch your mindset. You're no more doing machine learning, you're doing embedded software. And so now you have to look at what are the tools and processes for embedded software, and what is the best way to deploy.
Understood. Thank you so much for answering all those questions. Thank you so much, everyone, for coming, and thank you so much for Semir for that great presentation and for the great Q&A. That was great. Thank you again to our tinyML strategic partners for committing to take tinyML to the next level together. We'd like to thank especially our executive strategic partners, Edge Impulse, the leading development platform for EdgeML, Qualcomm, advancing AI research to make efficient AI ubiquitous, Sentient, accelerate your edge compute, and our platinum strategic partners, DeepLight, fastest video analytics solutions on ARM CPUs, Klikatech, global IoT solutions, Renesas, enabling the next generation of AI-powered solutions that will revolutionize every industry sector, Sony Semiconductor Solutions Corporation, and our gold strategic partners, Analog Devices, ARM AI, PhotoHub, Microsoft, NXP, SensiML, ST Microelectronics, Synaptics, and our silver strategic partners. Thank you, everyone, for joining, and we'll see you at our next event.